All right, I want to look at sections 5.1 and 5.4. So this deals with some of the basic integration. So this is a lot of the basic integration, the stuff that doesn't really require the U substitution. Also, it includes definite integrals and finding area under the curve. Okay, so the first objective on the study guide in 5.1 just says to find the antiderivative of a polynomial function. So you'll be given some polynomial, so you use the power rule. You know, if you have pluses and minuses like this, that you just can integrate term by term, and you can do this just using the power rule. So I would need a 4 so that when I subtract 1, I'd get a 3. So the power rule for integration is you add 1 to the exponent, but then you have to get rid of that 4. But the 6 needs to be there. So I'm going to multiply by a fourth or divide by 4, but I'm going to keep that 6. Okay. Here, to get a 4x, I needed an x squared. And you can do this by saying the 4 was already there. I need to divide out that exponent, 1/2 x squared. Let me write this a little different so I make it more clear where all that's coming from. So bringing down the 6, and then I'm thinking x to the 4th and knock out the 4. Bring down the 4, think x to the 2nd, knock out the 2. To get a 3, you had to have had an x there, and then put the plus c, and then simplify. So this would be 3/2 minus 2. 3/2 x to the 4th minus 2x squared plus 3x plus c. Okay. All right, and then they want you to do a basic derivative one. So you have to know your derivative. These you have to know. So you need to know how to do the antiderivative of cosine and sine. Okay. And then you need to know the ones that come from, that wind up having this as being the derivative. So you need to know what happens, that secant tangent x. You need to know secant squared x, right? And then you could potentially have cosecant and all of that, and those would just be the negatives of the others. So for instance, that to get sine, it had to come from cosine, but the derivative of cosine would be negative sine, so I need to make that adjustment. There'll be a negative there. Okay, cosine had to come from sine. Oops, I didn't mean dx, I meant plus c. Had to come from sine, and the derivative of sine is cosine, so I don't need the adjustment. Okay, and then secant tangent x is what you get when you take the derivative of secant x, and secant squared x is what you get when you take the derivative of tangent. All right, so those are not the ones that you see in section 5.8. Okay? So here we have a constant -5. I can just move out of the way. And then we have a basic recognizable trig function. We know that would have come from that would have come from secant x. Okay. Bring the -5 back in and put the plus c on it, and you'll be good to go. Okay. All right. So you'll have some like that are just pretty straightforward. They're not U substitution or anything like that. Okay. All right. The third one they talk about is to find the particular solution of the differential equation that satisfies the initial condition. So sometimes these are called initial value problems. Okay. So what you'll wind up doing on one like this is you're actually given, this is actually f prime of x that you're given, and you know that the value of f at 1 is 14. So the first thing you're going to do is integrate, okay, this right here. And when you integrate that, that's going to give you f. Okay. So you do that. So you know it'd have to be an x to the 3rd. So you need to get rid of the 3. So that really gives you a 6x to the 3rd. To get the 4, that had to come from 4x. Okay. All right. And this would be plus some c, some constant. It could be any constant. So there's infinitely many f of x's, okay, that would have the derivative 18x squared minus 4, and they'd be anything of this form, 6x to the third minus 4x plus some number. So what you're really being asked to do is to figure out what is this number. And that's where the extra condition comes in. See, f of 1 equaling 14 means x is 1 and y is 14. So what you're going to do is find out what is the, plug in the 1 for x. What is the value of the function at 1? So you plug in the 1 for x, and you know that right there should wind up being 14 when you're finished. So then you go from there, follow order of operations, or let your calculator do this for you if you're rusty on all that. 1 to the third should be 1. Then 4 times 1 would be 4. So I have 6 minus 4, which is 2. So I know C has to be 12. Okay. So then I go back, and right here where the C was, I know the particular solution. The particular one of these curves that I want is 6x to the third minus 4x plus 12. And that would be the final answer on that. Okay. All right, now we're also going to wind up having to do definite integrals. So this is 5.4. So let's go ahead and look at those objectives from the study guide. So in 5.4, we're being asked to evaluate a definite integral of a polynomial. So that would be kind of like number 7, but it could be a messier polynomial. It could be an x to the third plus 2x minus 5 or something in there. But you could handle it in a similar way. So this is a polynomial, and I'm going to find the definite integral. I've got those bounds, that -1 to 5 thing. Don't really need to use a u on this one, okay? Because the derivative of x is just, x plus 2, is just 1. So I'm just going to wind up doing the integral, and I would get 1/2 x squared plus 2x, and then I'm going to evaluate that from -1 to 5. So I've done the integral. That means the integral symbol is gone. And now I use this bar, and I'm telling people I'm going to now evaluate that expression from -1 to 5. So you do the top, minus what you get when you plug in the bottom number. Hardest thing about it is all the signs. People make a lot of mistakes with this. Okay, so that would be 25 over 2 plus 10 minus parenthesis. In here, this right here would be +1. -1 times itself would be +1 times 1/2. But 2 times -1 would be -2. Okay. So let me go ahead and put these together. So if this is going to be 25 over 2, if I'm doing it by hand, I'm thinking about 10 being 20 over 2. So this would be 45 over 2. I don't need parentheses really. Then I have minus, and then right here, 1/2 minus 4/2 would be minus 3/2. Or think about it like a mixed number. You have 2 that's negative, and you're adding up 1/2. You'd be at -1.5, -3/2. But there was a minus a negative. So that's really 45/2 plus 3/2, which gives you 48/2, and that winds up simplifying to just be 24. Now, a lot of times they don't turn out to be just that nice. They'll have all kinds of fractions in them, and that's just fine. Okay? All right, then it says to evaluate the definite integral of the trig function. Well, I forgot to write that one down. I'll do that after I do number 8. I did a complicated one. I'm not sure yours will be complicated, but we'll look at the one I gave you at the end of the test. All right, so let's go ahead on this and do the area of the region bounded by the graphs of the equations. So the way I worded it on my test is I said find the area of the shaded region, and I gave you this picture. But the way they worded it here, you need to realize Another way to ask that question might be to find the area of the region bounded by the y equals x squared plus 3, the vertical lines x equals 0 and x equal 2, and then the x-axis, which is y equals 0. Okay, so that would give you this figure. And there's no succinct area formula, for an irregular shape like that. That's the beauty of integrals. They allow you to get the area under that curve. So you just need to set up an integration problem. You want to integrate x squared plus 3 with respect to x. Okay, and you want to do that, and here's where these bounds come in, from 0 to 2. Okay. All right, so I'm going to go ahead and wind up, we're undoing this, and it's just a polynomial. So I'm going to wind up getting an x to the third and getting rid of it using a 1/3. What I was hesitating for is I was thinking, back here, I was telling you it didn't really matter if you did a u because it's just a little polynomial. And I had said something like the derivative of that would just be 1. You got everything you need. Okay. Even here, it doesn't matter that the derivative of the inside would have been 2x. That doesn't really matter, the fact that we don't have a 2 or anything, because we're just going to integrate term by term. Anyway, but that's what I was pondering when I was hesitating. All right, so this would be x to the third with a 1/3 out in front plus 3x, wouldn't it? And we need to evaluate that from 0 to 2. So we're going to wind up plugging a 2 in everywhere, and then going back and plugging in a 0 everywhere. So this would equal the 1/3 with the 2 cubed plus 3 times 2 minus 1/3 times 0 cubed plus 3 times 0. Well, this one was kind of nice because that's just 0, not goes to 0, but it equals 0. This one right here would be 1/3 times 8 plus 6. So that's 8/3 plus 6. 6 is really 18/3. So that would give you, let me write that a little differently. So that would be 8/3 plus 18/3. And so you wind up with 26/3 for your answer. And just thinking about that, that would be 8 2/3. All right, and looking at this picture that we had here, okay, 8 2/3. That rectangle there would have been 7 by 2, would have been 14. It is above the x-axis, so it is a positive value. And, when you look at that, this kind of cuts off a big amount. If it had been this diagonal right here, instead of what it was, then you could estimate that area on that part right there to be half of 14, which would have been 7, but you've got a little bit more right here. I just sometimes do that kind of thinking to see if I'm on the right track or if I maybe had a mistake with my negatives or my setup. Okay. But anyway, you just really do the integral and you'll be good. All right, so the one thing that I forgot to do is the definite integral of a trig function. So let's go ahead and do that. There was one of those, but I put it at the end after you had done some of the integration by substitution. So I'm going to go ahead and look at it now, but it does kind of require you thinking about integration by substitution. So here was the question. All right, so our first job is to get the thing integrated. So it looks like we should use 4 plus 3 sine x for our u. If we do, and we do the derivative of that, the derivative of 4 would be 0, then we'd get 3 cosine x dx, okay? So we have 3 cosine x dx, and it doesn't have a negative on it because when you do the derivative of sine, you get cosine, okay? All right, so right here, I see the cosine x dx. I'm going to be able to replace the cosine x dx with 1/3 du, aren't I? I could divide that 3 out of the way. Okay. All right. So I've really got, I'm going to rewrite this now. I've really got 1 over u to the third, and then I've got 1/3 du right here. Okay, and I'm not going to put the bounds on that yet. So I'm going to bring the 1/3 out. I'm going to rewrite this as u to the -3, and I'm just going to do the integration now. So I would add 1, which would give me -2. Need to divide by -2 or multiply by -1/2 to knock that out, and then don't forget the 1/3 that you already had. So when I integrate that, I would really get this, right? But we don't have to worry about the c's because we're going to be doing the definite integral, so we'll be able to knock those out anyway, okay? But it's okay if you think about it at this point, but really you're going to be evaluating this, okay? So let me clean this up a little bit. I might write that u back in the denominator since it's a negative exponent. Think about it like that. Now here's what I can do at this point. I can think about what the bounds should be on that in terms of u and put those on it. So here's what I'm talking about. One option, these right here are x's right now. If I wanted to do the u's, I could use the fact that u equals 4 plus 3 sine x. So I could do u of 0, and I would get 4 plus 3 sine 0, and sine of 0 is 0, so that would equal 4. And then I could do u of pi over 2, which would equal 4 plus 3 sine pi over 2, and the sine of pi over 2 is 1, so I would get 7. So I could switch, I could change the variables, and once I get into u's, I could, instead of having to go back to x's, I could use the 4 and the 7 as the bounds on my integral, okay? The 4 and the 7. So then when I am evaluating, I'm going to evaluate from 4 to 7. I'll show you the other way too, but you could do that. So then you'd wind up getting this to be -1 over 6 times 7 squared minus -1 over 6 times 4 squared. Okay. Now my calculator could not handle keeping this in fraction form, so I did it by hand to get the fraction form. So I knew my common denominator would need to have a 6, a 7 squared, and a 4 squared on these. Okay, so that meant I would need to multiply here by 4 squared and multiply here by 7 squared. Okay, so I'll get -1 times 4 squared here. And over here I have -1 times 7 squared. Okay. And I wound up then getting on this, I left the denominator in factored form like that for a minute, but I just worked out the numerator. So this would be -16 minus -49 all over that denominator. And then I worked it out. So that numerator became 33 over this denominator. Normally a calculator can do all the simplifying for you, but it kept coming back as a decimal. So I just did it like this. And then I like to simplify. I noticed the 3 will go into 33 and into 6. Then I worked it out, and my denominator was 1568. And then if you did it using a decimal, that was okay. It wound up being about, and I didn't specify how to round, but it should turn out to be about 0.007. Okay. So that approach had me changing the bounds on my integral from x's to u's, so I could use just be here and use that. It works the same. It's just as good if you wanted to put the x's back in like that and evaluate that from the original 0 to pi over 2. So feel free to do that if you prefer, okay? So if you did that, it's like you'd be calculating the value of the sine function at the pi over 2, and then subtracting from that this. Squared. And so you'd still get the negative 1 over 6 times 7 squared here, because sine of pi over 2 would be 1. And here you'd get 6 times 4 squared, because sine of 0 is 0. And then from there, you already saw how we worked it out. Okay, so that was covering the 5.1 and the 5.4 off the study guide. And the last problem I did actually did involve U substitution. The problem that's on the study guide that said evaluate the definite integral of the trig function, I'm not sure whether those are going to have the need to do a U substitution or not. 5.4, in 5.4, you really didn't know U substitution yet. So they may be easier than this example.